Hi, Vicky.
Hi, Shane.
Have you ever had to use a fire extinguisher or otherwise put out an unplanned fire or something like that?
No,
No.
no, I was thinking about it and then I got lost in the thought of how bad of a reaction I would probably have if I was in that situation.
Like the
I feel like I would just run around in circles.
you'd be bad at emergency response
Yeah,
on the
just like
fire.
waving at it or yeah. Why do you
Oh
ask? Have you done
goodness.
that?
Well, so the unplanned fire part, not necessarily.
Mhm.
I actually I love fire from a like a bonfire type perspective.
Creepy.
I'm not like causing unplanned fires or anything like that. And the Boy Scout Eagle Scout in me is actually quite responsible when it comes to fire.
Okay.
So I've been fortunate from that perspective. But I do from the fire extinguisher part.
Uh-huh.
Caveat: it was not me. But
Mhm.
when I was a freshman in college, I was in a dorm with a bunch of freshman boys. And I forget exactly why or what led to this, but one night, a Friday or Saturday night, there was this ruckus that erupted in one of our common rooms. And I was like in my
No.
room and just heard screaming down the hall. Not like, not horror. Oh my gosh, this is bad screaming. Just eruption of noise.
Excitement.
And I ran down the hall and someone or someones had unloaded one of the like chemical fire extinguishers.
Oh,
There
no.
was in the hallway, they had the long hose
Right.
and basically put it under the door and unloaded one of them into the common area as a practical joke to pull on someone. And what they didn't know is that all of this stuff is synced up to all of the emergency response type stuff. And so our dorm ended up having to be evacuated, not because there was a fire that someone put out, but because someone used the fire extinguisher when they weren't supposed to, and it alerted
Like set off
emergency
all the
response. And our building, so this was in Pitt, and it's part of like Pitt has this huge hospital system. Our
Uh-huh.
building was literally attached to the hospital, and so folks were there in 2 minutes. And so we got evacuated. Everyone on our floor got in trouble. We got reprimanded. Our
Uh-oh.
our building ended up being we that was one of many incidences we actually had. We by the end of the year, we had kind of security patrolling our building every weekend because we had a bit of a reputation. But yeah, so again, I cannot stress enough that this was not me, and I'm not just saying
We
that. I
believe
wouldn't bring
you.
the story up if it was me, but I was adjacent to the unfortunate effects of using a fire extinguisher. Let's say when you shouldn't, you shouldn't.
When you shouldn't. Yeah. So did it, like, set off sprinklers or anything, or it was just attached?
No,
Oh,
no,
good.
the system's just all linked together.
Oh,
Yeah, it didn't do, but it did
of
damage. I mean,
course.
it's this fine particulate. They had to completely get rid of all the furniture, do all sorts
Sure it
of
was, like,
other
an
clean. Yeah,
event.
it was a big deal. Yeah,
Yeah.
so if nothing else, I learned what that actually looks like and why you shouldn't mess around with it.
Yeah, so don't do it.
Don't do it.
Moral of the story.
Science is fascinating, but don't just take my word for it. Join us as we hear stories from scientists for everyone. I'm Shane Hanlon,
And I'm Vicky Thompson.
and this is Third Pod from the Sun. All right, so that was us talking about fire on Earth, or specifically in a dorm room. But what about fire in space?
Well, what about it? There can't be fire in space because space is a vacuum, right?
Wait, so you're telling me that Star Wars was wrong?
I obviously have no idea what you're talking about. Star Wars.
Oh, go back to our previous conversation about how Vicky
Yeah.
doesn't watch any sort of
I
fantasy
don't yeah.
or science fiction.
So I guess there's
That's okay. That's okay.
okay.
So, so no vacuum in space proper. But what about inside ships and habitats that just happen to be in space? So to enlighten us, we brought in producer Sara Whitlock. Hi, Sarah.
Hey, Shane.
Tell us about fires that follow us from Earth into space.
Right. Fires really do follow humans around because there isn't oxygen hanging out in space. So, pretty much the only places that you're going to have fire in space are the spots where humans are creating an atmosphere just like the one that we have here on Earth.
So that's like spaceships, space stations, future space colonies.
Right. And that sounds like it could potentially has been a problem and could be a potential problem for the upcoming Artemis missions. So let's get into it.
My name is Augustin Guibaud. I'm an assistant professor or lecturer at University College London, so I teach and do research at the same time. I teach in civil engineering on structure design and how to integrate different problems, and my main research focus is in fire safety. Study fire safety in complex environments such as spacecraft or historic buildings or even in the wildland, the urban interface.
So how did you first get started in spacecraft research? That seems like a cool niche to be in.
That's a very cool niche, and it was, I would say, a story, based on luck and just opportunities. So at the end of I studied engineering and applied math, and at the end of my studies, I really wanted to do a PhD. That was more of a stubborn obsession than a real call for research at the time. And I was just, going through some proposals that were out there, and I saw one that was about fire and spacecraft, and I was combining these two very cool things that I had always been curious about, and the combo proved to be even more amazing than what I ever thought. So I joined in 2016 a research institute in France called Jean Le Rond d'Alembert, and Professor Guillaume Legros, who was at the time leading a project to study flame spread in microgravity, so with the hope of improving how we do fire safety in spacecraft. At the time, I was doing a lot of experimental work, so we were burning samples in weightlessness and trying to see how oxygen pressure or flow velocity would affect the way the flame would spread. The idea is that you can't really shut it down or turn it off. It's not a button that you can say, okay, no gravity now. Otherwise, we'd have, I think, amazing, cool rooms around the world to provide you with that experience. So what we did was crazier than this. We were going in this aircraft that does parabolic flight. So the very simple principle is that you're falling, like free falling towards the ground in an aircraft, and that helps you get up to 20 seconds of weightlessness, and you're literally flowing inside or flying inside the aircraft. So we could do experiments like this and repeat them very regularly. And then we changed conditions to understand, what could help prevent fire spread, what could reduce the amount of smoke you produce, what could be the optimal conditions for anyone flying a spacecraft.
What sort of conditions do you need for a fire to start?
So you might be familiar with what we call usually like the fire triangle, which is a simplistic but very, I think, like very useful way of understanding what you need. For a fire to happen, you need something to burn. So you need a fuel, you need an oxidizer too, so you need oxygen, and the last thing you need is a source of heat. And so if you think about what happens in space exploration, we have usually two types of objects that we send out of the atmosphere. One is satellites, and satellites can have fuel, and they can have sources of heat, such as electrical current or anything like this, but they do not have oxygen, because you do not need oxygen unless you put a human somewhere. And so this is why in a spacecraft, you now have these conditions where the fuel is going to be anything from some technical material that you need, but also, just the clothing of the astronauts, or some things which are just there for comfort, such as paper or any kind of stuff, any kind of polymers that you may have, which have not been tested for fire. You have oxygen because you have your astronauts, and you have also electrical sources of oxygen, also chemicals that can react to create the heat that you would need at the beginning. Space is a very unique environment for this, because we are sending humans which are so vulnerable in such an aggressive environment that there's so many constraints. There's so many ways things could go wrong. Fire is just one of them. So you can't put this as the utmost priority. The utmost priority is to make sure your mission succeeds and everyone comes back alive. And so then fire is one of the variables that you need to adjust in this environment.
Oh yeah, that's terrifying, just to think of being stuck on the spacecraft with no way to get away from the fire.
But there's also some fundamental changes in combustion, which is why, for instance, what I was working on in my PhD, where the flame response to the absence of gravity is different. So gravity plays a role in combustion. It has a major effect on the way it burns. If you just think about a candle, so if you are to light a candle, it seems very natural to think, the candle is pointing upwards. It's only pointing upwards because once the gas are heated, they get lighter, and so they go towards the top. And so you have this very elongated shape of a flame. But then you can start to get into, much deeper questions about, just really looking at the candle. The candle doesn't have a uniform color. It's much brighter at the center. It's kind of like orange at the top, and it's blue or almost transparent at the bottom. And what you're actually seeing here is that you have a visual representation of a sequence of chemistry. You can see that there's different things happening at different moments, and it's all dominated by the fact that the gravity is pulling the candle upwards. Now, if you're in space, gravity disappears. And so one very simple question for you is, what do you think your candle looks like?
Is it just a circle then? Yeah, what happens?
It is. If you have no movement of air around, it's going to be a perfect sphere. And you have this amazing picture by NASA that was like a shot of a candle in microgravity. And you see this very almost calming, because I've been maybe provoking some panic so far. So if you want to see a calming image of a fire in spacecraft, just look at this picture of NASA. It's like this very nice, not so bright blue sphere of a flame. And this is what you would see in a space environment without any movement of air. And so the very fundamental thing here is that the flame without gravity cannot produce its own airflow. So it's not creating this kind of movement where oxygen is going to be drained at the bottom, gas are going to be ejected at the top, and you have now this kind of sphere that tries to expand because it has to go towards the oxygen to be able to consume more oxygen. But the fundamental thing in what I said is that you need to have no air movement to have this type of situation. The moment you introduce any kind of ventilation, then this symmetry is broken. And the flame is going to follow the air that you have around, and you're going to have now oxygen flowing towards your flame. So you're going to have oxygen that is fueling your flame. And in a spacecraft, because you need ventilation for the astronaut to breathe, otherwise you could just have like pockets of CO2 building up where you breathed before, which is not exactly ideal if you want to be able to rest and sleep for a few hours. You have permanent ventilation. So anywhere you are in the spacecraft, you're going to have these movements of air that are actually going to affect your fire. And so what we try to study, and this is kind of like back to my PhD, what we are studying is what happens when you have this kind of airflow that is quite slow. And so it's under the acceleration that you would see on the Earth when you have a flame. And you try to understand how it's going to affect the properties of your flame. And one of the things that we saw is that at these slow speeds, at least in the configuration we were studying, you produce a lot more smoke. And that kind of like back to what exactly is smoke. And that's another question that I could talk about for hours. So I'm going to try to keep it short and fairly easy to understand, or I hope easy to understand. But when you see smoke, what you're seeing is fuel that didn't burn. So these kind of like black traces of soot that you can see sometimes, this is bits of carbons that have been aggregated together, and they form inside the flame. And so inside the flame, they start to form. And when they meet oxygen, if they are at a high enough temperature, they immediately react and they disappear. And they produce heat in the process. And this is what happens in your flame. Now, when these particles are inside the flame, if they are hot enough, they emit light. So they radiate. So these particles are the reason why your flame is yellow. And they actually explain why your flame is not bright at the bottom, but brighter at the top, because at the bottom, they haven't formed yet. And as you go up in the flame, they form and they get brighter and brighter because the temperature increases and they start to emit light. Now in a flame, what you see is at the bottom, it gets more orange and a little less bright. It is because as they radiate or as they emit light, they lose energy because energy is leaving the flame through this light emission. And so at the top, you've lost energy. The temperature goes down, so it gets more orange because it's cooling down. And if it's too cool, it's kind of like too cool to burn. And so it's just going to escape freely in the atmosphere. You can also observe this like just on Earth with a candle that's producing smoke. You see this kind of like trail of smoke coming out of the flame that goes from a very bright yellow to more orange colors and then gets dark. And what we saw is that if you are in spacecraft or if you are in a flow that is slower than what you have on Earth, then these particles have a lot more time to emit light. And because they have a lot more time, then they lose a lot more energy. And so what happens at the end is that you have situations that are a lot more in favor of smoke emission than what you had on Earth. And that's, again, a problem because you are in this one environment where you cannot open a window. It's already a problem if you're just trying some new cooking techniques at home. And so just imagine what would be the case if you're like in this spacecraft with new materials, no way to open the window and just some flames burning around. And so that's a problem that we really wanted to investigate to find the optimal balance between oxygen content and pressure so that a human can breathe. And at the same time, you minimize the risk of smoke in spacecraft.
So it turns out that not only are fires in space very likely, they also behave way differently than fires do here on Earth.
Yeah. And my question is, what do astronauts do if a fire actually does break out?
Those are both good questions. There's actually a couple firefighting tools specific to fires in space, and some of them actually take advantage of unique features of the space environment.
You have to balance actually a lot of different objectives. When you think about a fire risk or hazard, you have this entire genre of hazards you're actually getting into, because you have the problem of flammability first. Is something going to burn or not? Then you have the problem of fire spread. How fast is it going to burn? Do you expect a big fire in a few minutes, or do you have more time to respond? And then do you expect a lot of smoke or not? And these are three very different avenues of problems that you need to tackle at the same time.
Wow.
Most of the time we end up doing compromises in these type of things. So in a building, in everyday life, you don't usually you don't focus so much on flammability, because you don't care so much that something's going to catch fire. I mean, this is what happens with most clothing that you may wear. For instance, some clothing can catch fire. You just don't expect to be in a situation where it's going to happen, or that if it's going to happen, it's not going to burn in the bat of an eye. You know that you're going to have enough time to remove it. What we focus a lot more on the ground is this question of fire growth, making sure that the fire cannot have a critical size too fast. And this question maybe of smoke emission, that you want to make sure that you will not have pollutants or toxic species being released. When you're in a spacecraft, you all of a sudden need to focus on all three avenues at once. So that can be more of a problem.
So what are some of the options that people have come up with so far? Now it sounds almost impossible to be able to put a fire out.
So there's been a lot of, I'd say, good brains. I'm definitely not talking about mine, but people who have been actually in the space programs developing solutions. And if water was a very tempting solution, they've developed things that are closer to water mists or water foams now. So the idea is that you just want the foam to prevent the fire from spreading. You're cutting the access to oxygen to the fire. That's kind of the principle. That's how you break this fire triangle. And you have this foam, so it's a solid state, or something that will not be able to contaminate most of the components. Another solution that is developed is gas-based extinguishers. And today, after decades of development, the one that is used in the ISS, for instance, or one of the systems used in the ISS is CO2 extinguishers. So you use carbon dioxide because you know that it's not going to be toxic beyond a certain amount to the human body. So you can easily keep this in the system afterwards. And you also know that CO2 is going to remove the oxygen. And so it's going to, deplete the fire from this oxidizer source. So you just want to kill the fire by preventing it from being fed with oxygen. That's one way it's envisioned now. There's also some systems that are being developed now with nitrogen. The idea being that if you have an atmosphere that combines oxygen and nitrogen, you may want to be able to temporarily increase the amount of nitrogen if at the same time astronauts are just wearing some breathing apparatus or just some oxygen masks, so that in the environment the flames die out, and then you can increase the amount of oxygen relative to the amount of nitrogen in the capsule. It's kind of two ways that are envisioned at the moment.
Wow, yeah, that's really cool. Very unique compared to Earth, where you can't just change whatever the atmosphere is.
It's true. At the same time, it all relies on some things that also trigger more problems, because one of the things we're used to is, just open a door or a window and you know that the smoke's going to go away, for instance, and you can just make sure that you equilibrate everything. Now, I just remember this quote, which is very simple but pretty striking, from Lazutkin. And Lazutkin, one of the cosmonauts who was in the Mir space station in 1998 when a fire broke out. And what he said was that for the first time, he realized he could not open a window. And that was something that all of us again can trigger a lot of anxiety, because you're realizing that either you face the solution or you have a much bigger problem. You can't just run away this time. Whereas most of the strategies we have in cities or in buildings is egress. You want to make sure people can run away. That's the 101. That's why you have all the escape routes on building. You just have something where if you face a fire, you have the extinguisher and nothing else. That's first you try the extinguisher, but most likely you can run away. That's something that's fundamentally different in a space environment.
It sounds like there are at least a few firefighting tools in case astronauts do need to deal with a fire.
That's right. Unfortunately, a lot of those tools and strategies were designed on the International Space Station in low Earth orbit. Travels in deep space, like the Artemis missions that are heading back to the moon, have extra fire challenges and need new approaches to fire safety. Dr. Guibaud laid out those challenges in a paper he published this year.
Yeah. So if you think about Just first, remind. So when you talk about deep space, it's anything that's going beyond the low Earth orbit. And we say low Earth orbit, it's already quite high, but it's a few hundreds of kilometers. You're basically close to home. You can think of this as you are in your backyard. So if there's a problem, you can come back. You can get an escape pod. You can go back to Earth. You can get some resupply. The logistic chain is not broken in a way. If you want to go to Mars, it's a 6-month journey. It's a whole different thing, and so it's really if you're running low on something, you can't just just stop on the side of the road, put on the warnings and wait for a resupply mission to come. You have to be fully autonomous, and that's already a change in the paradigm of how you can manage your fire safety. You will not allow a fire to happen in these conditions. You cannot tolerate a system that is not redundant, because imagine you're facing a fire after 3 months and you have to use any kind of fire extinguishers that you have. Will you then continue the trip knowing that you've depleted your resources, or will you have to come home? And that's one of the problems that you may have, this pure logistics problem of distance, because we are talking at a very new scale, something we're not used to. There's some inherent problems that are associated with deep space. One of them is oxygen, just recirculation, or just how we can recycle oxygen. At the moment, if I'm not mistaken, our capacity is around 40%, which means that less than half of the oxygen that is used in the spacecraft can be recycled internally. We're able to break the CO2 into molecules that, again, give you some oxygen. But we need to pump these numbers up if we want to go much farther, because otherwise you're going to have to basically have the small capsule and then the amazing resources of oxygen at the back of the truck, in a way, to go all the way to Mars. And so that also means that you're going to have very high concentration of oxygen somewhere stored. And that's a new risk that you didn't have so far, or that you didn't have to face so much.
Does that mean that the astronauts are just going to have to live with a lot of risk?
In a way, yes. But when it comes to fire safety, if you think about it, we're always working in a risk environment. So there's always this question of accepted risk. And what I think is going to happen, or what I hope is going to happen, is, of course, we're going to have more risks out of a lack of understanding of the situation for the first few missions. But to compensate that increased unknown, there's going to be more systems or more redundancies, or more efforts put towards the understanding of what a fire could be. I've had the chance to chat a few times with a range of different astronauts, and what you see is that fire safety is part of the training. It's a very it's one of the parts where they really know what systems they have on board. They have procedures, and these procedures might not be perfect, but you're sure at least that you're not going to be caught by surprise in these kind of situations. One of the strategies that was implemented, for instance, in the International Space Station, and that will likely be implemented also in the future, is a strategy of compartmentation. And what you're doing is you're making sure that you can always shut the door between two volumes, so that if a fire starts somewhere, you can shut the door, you remove the oxygen, and you may have lost, a lot of oxygen in the process, and you may have damaged some infrastructure too, but you can then just refill this module, and you make sure that the rest of the station is safe. And so this is where, going back to the deep space question, this is where the further you are from Earth, the more problems you're going to have to actually resupply or repair what you've done before. That's a part of the fire strategy that is sometimes ignored, but that needs to be really thought through, which is the cleanup phase. You had a fire. How do you make sure you can get back to the situation pre-fire? And that is the one that is the most resource consuming most of the time, even on Earth.
Yeah, wow, I can't even imagine what a cleanup of a fire in space would look like. I don't think there are enough wet wipes on the International Space Station to be able to get rid of all the soot or things like that.
That's a moment where usually they consume quite a lot of the ventilation system or the filters. So you need to have a lot of filters back to be able to make sure they're not completely clogged or polluted.
Yeah, wow. And then the last question that I had was about radiation. I'm a little confused about how radiation from deep space would interact and...
There's a role in fire. One of the thing maybe, or one of the thing that can be understood is radiation is the number one danger when it comes to deep space today. Fire is almost secondary to it in the process, because fire is a risk, and you're going to have a probability of a fire happening during a certain amount of time. Radiation is almost a certainty, or is a certainty. What happens is, if you are in low Earth orbit, you are protected by the Earth's magnetosphere. What it means is that radiation coming from the sun or radiation coming from outer space beyond the solar system are stopped or deviated the Earth magnetic field. If you go beyond this magnetic field, which is what's going to happen if you want to go, for instance, to Mars, even I think if you are on the moon, if I'm not mistaken, you are exposed to these radiations. The problem here with fire or the interaction with fire is twofold. One is we have very little knowledge of how material that has been affected by radiation reacts in case of fire. So you may have some materials that have been boosted with chemicals for fire-resistant properties that will not age well at all in case of radiation or regular radiation exposure. And so you find yourself in a situation where you may have a deteriorated fire resistance of your environment because of radiation. The second one, which is back to the Apollo 1 situation, is a situation where you are trying to protect yourself so much from radiation that you forget some of the fire priorities. One of the materials that has been sometimes brought up as a good radiation shield is polyethylene. And so polyethylene is one of the materials that we study. It has a very poor performance in fire. It's something that has a lot of these like carbon-hydrogen links that are very good for combustion. And so this is something where you may put so much emphasis on this primary threat that you actually turn a secondary one into a time bomb. So this is something where we try to keep track of what's happening in the radiation community in terms of solution. There's also other solutions that are very good and that are perfectly neutral from a fire perspective. And what we want to make sure is that these are the solutions that are going to be ultimately promoted.
Gotcha. Wow. Even more facets of things that could go wrong and could cause fires in deep space then.
Well, one thing I want to say is that it's an exciting endeavor. I don't want to give anyone the idea that they're getting in a giant scale barbecue if they try to become an astronaut. I think it's a matter of risk again, and we've seen so many successful missions, and we've seen so many situations where I think went perfectly that us as people who study fire, we are usually focused on what went wrong. But if you think about the frequency of accidents and anything like that, so we're trying to do our best to lower these frequencies. And what we want to make sure is that everything's going to go fine. So if anyone has aspiration to be an astronaut, I hope that they only have more envy to go on the moon in this very safe environment that we're going to try to provide, and they don't get deterred by what I said so far.
Even though it kind of does sound like potential for a big barbecue, I'll take him on his word that it's not.
It's not. Yeah, I'm glad he clarified that. Fire was the one thing keeping me from becoming an astronaut. Had my application ready.
Yeah, I can't even imagine. I do not want to be the person that has to wet wipe down the space station after it catches on fire. So I hope he's right.
I could just imagine just like thousands of packs of wet wipes, just like a little bit here, a little bit there. Yeah. Thankfully, that doesn't seem to be the case. And with that is all from Third Pod from the Sun.
Thanks so much to Sara for bringing us this story and to Augustin for sharing his work with us.
This podcast was produced by Sara with audio engineering from Collin Warren. Artwork by Jace Steiner.
We'd love to hear your thoughts on the podcast. Please rate and review us, and you can find new episodes on your favorite podcasting app or at thirdpodfromthesun.com.
Thanks all, and we'll see you next week.
I had a big fire when I was in college, actually. And the smoke damage, to imagine that the smoke damage in the space, in space
or
wherever is worse than typical
like a house
smoke
fire?
Damage. Yeah, that's hard
Jeez.
to, yeah. Someone kicked their blanket into an illegal candle that they had. Yeah. And
this is why you don't have it's not just because they're being hard about it. This is why you don't have open flames.